if you misinterpret even just like a single word on a modern manufacturing floor, a multi-million-dollar piece of machinery will literally tear itself apart in, well, milliseconds. So today, we're doing a deep dive into the really unforgiving language of precision engineering.
Yeah, exactly. We're using this bilingual technical deck on mechanical vocabulary as our guide today. But, we aren't just looking at dictionary definitions. We are tracking 5 core machining terms.
Right.
And these terms act as the physical, sequential steps that basically dictate system performance in both R&D and manufacturing.
So let's look at how raw metal gets its basic shape first, right?
Mm-hmm.
The deck breaks down this term called turning. And to put the stakes in perspective immediately, our source highlights maintaining a plus or minus 5 micron tolerance on an input shaft.
Which is incredibly tiny.
Yeah, I mean, for context, an average human hair is, about 70 microns thick? You are slicing away just a fraction of a hair's width of metal so a high-speed bearing doesn't rattle itself into shrapnel.
Right. And the mechanism making that possible is the specific kinematics of turning. So the workpiece itself is spinning at incredibly high speeds while a stationary cutting tool moves against it.
Okay.
Because the axis of rotation is fixed, it is mathematically perfect for creating true cylinders.
Which makes turning essentially like a high-speed potter's wheel for metal.
Exactly.
But, it seems like with the advent of modern 5-axis milling, turning might become obsolete. I mean, since a mill can carve almost anything.
Well, you'd think so, but turning actually remains vastly superior for that absolute concentricity and surface finish on round parts. Milling flips the kinematics entirely.
How so?
So in milling, the workpiece is stationary, and a rapidly rotating cutter feeds into it.
Okay, so taking that potter's wheel analogy further, milling is more like a sculptor's chisel.
Yes.
Except I guess the chisel is spinning at 10,000 RPM.
Yeah, that's a good way to put it. And because the workpiece is fixed in place, you can attack it from multiple angles. That 5-axis milling setup mentioned in the deck.
Oh, right. The one for the aluminum housing?
Yeah, that's what allows the cutter to carve out really asymmetrical, intricate internal geometry on an aluminum housing. So complex contours and flat surfaces that are just physically impossible to create on a spinning lathe.
Gotcha. But hitting a 5-micron tolerance on the outside doesn't really matter if your internal connection points are slightly off, right? So once you've milled that complex housing, you still need to attach it to the broader system, which brings us to drilling and boring.
Right.
And I often see manufacturers trying to cut costs by relying solely on high-precision drilling to create, say, a bolt pattern on a mounting flange. So why add the extra cycle time for boring? I mean, isn't boring just like drilling a bigger hole?
Oh, it's definitely not just drilling a bigger hole. The main reason is tool deflection. So a drill bit naturally wanders. Drilling gets the initial hole punched through the material really quickly.
Right, it's fast.
Yeah, but the bit can flex under pressure, and that leaves a slightly off-center hole with kind of a rough surface finish.
Oh, wow. So you can't rely on drilling alone if you're trying to fit a high-speed shaft perfectly through that hole.
You absolutely cannot. Boring doesn't just widen the hole. Its rigid single-point cutting setup reestablishes the true geometric centerline.
Oh, I see.
The source actually notes that boring is mandatory for achieving the submicron concentricity you need to fit bearings securely.
Because a standard drill just can't physically deliver that stability.
Exactly.
Okay, so you've got your perfectly concentric bored holes, your turn shafts, your milled housings. You are finally ready to bolt this whole assembly together. But there's like a final critical step before any of that happens, which is facing.
Yeah, facing. It's the process of cutting a part's end face, so it's completely flat and strictly perpendicular to the axis of rotation.
But wait, if we've already employed these ultra-precise 5-axis mills and lathes to shape the part, it feels a bit redundant to treat facing as a separate critical hurdle. Wouldn't the ends already be flat enough from the previous operations?
Well, flat enough to the naked eye still leaves these microscopic hills and valleys in the metal. Think about a gear casing under immense pressure.
Okay.
When two metal components bolt together, any microscopic tilt or unevenness means they won't sit perfectly flush.
Ah, so you're talking about assembly integrity, like if those faces aren't perfectly perpendicular, you just don't get a true seal.
Precisely. And in a high-stress mechanical system, that perfectly flat face is literally the only barrier preventing a catastrophic lubricant leakage once the machine is actually running. The facing process is what guarantees that flush seal.
Wow. So turning, milling, drilling, boring, and facing, these aren't just, technical vocabulary words on a bilingual spec sheet. They are the brutal physical laws of modern manufacturing.
Yeah, they dictate whether the machine you rely on functions smoothly or just fails entirely. Every single mechanical system you interact with today depends on these sequential processes working perfectly in concert.
That's incredible. So the next time you see a flawless, leak-free mechanical device, whether it's the transmission in your car or maybe a hydraulic pump on a construction site, ask yourself this: which invisible submicron machining process was the hardest to achieve to make that perfection possible?